Alright, here we go. Take home number 8. A little different format. You're actually trying to kind of solve a problem here, which is kind of cool. Not that you weren't previously, but this one has a little context to it, which makes it kind of fun. Fun if you're a math nerd. So you've got this piece of paper, right? The text box is 24 square inches. So you got x and y. So you need to make sure that x times y. This is a non-negotiable. X times y is 24. So you get to adjust the dimensions of this text box as you want to. But what you're going to try to minimize is the actual amount of paper that you use. Okay, so what I have here in green, you can make that green area as big as you want to, but you actually want to minimize it. Okay. So a big part of this problem is just understanding what they're asking. So what's the mathematical formula that tracks the that green shaded region? So let's say it was like area as a function of x and y would look like, let's see, this whole length here, that's x plus 3, and this is y plus 2. So it's x plus 3 by y plus 2. And you can rewrite that formula if you use the fact that x times y is 24, which also means that y is 24 over x. You can write this area formula just so it's a function of x. So you got x plus 3 times 24 over x plus 2. And certainly if you wanted to multiply that out, you could, to simplify it, and maybe we will do that. Right, so x plus 3, 24 over x plus 2. This is just another way of multiplying that out, kind of organizing it. So 24 over x times x is just 24. 2 times x is 2x. 24 over x times 3 is, what, 72 over x? And 2 times 3 is 6. So what do you got? A of x is 2x plus 72 over x plus 30. So there we go. That's the function that's going to track the area of that green paper. And I think that's actually prompt 1. Determine an equation called a of x that you will minimize to answer this question. Note you'll need to use a secondary equation to get a of x. Well, that secondary equation was x times y is 24. So here we go. We got a of x is 2x plus 72x to the negative 1 plus 30. Now x, right? X is a length. So let's think. What's the domain of a of x? And you think as you start to plug values of x into this, you're going to want to say, well, what makes sense for x? So what's the smallest that x could be? Okay, well, x couldn't be 0, but it could be infinitely close to 0. And it couldn't be, could x be, 240? Well, certainly, right? Because 240 times what is 24? Now I'm going back up to this equation. Right? Could x be 240? Yes. If x is 240, y would just need to be 1/10. So how big could x be? Well, it could be really as big as you want it to be. So x is going to go from 0 to infinity. Alright, so there's our equation. That's where x lives. And that equation is going to track that area of the green there. And just to show you where it comes from, I had some students start this in class, and they said, well, if you want your text box to be 24 square inches, what if you made it like 8 by 3? Let's do this real quick. So if this was 8 by 3, what would the area of the green be? Well, 8, and then you got to tack on 3 for these two distances. So 8 really is 11 here. And then 3, you got to tack on an inch each side, so that's 5. So 11 by 5 is 55. So we used an x of 8. Let's plug 8 into our a of x formula and make sure it works. Right? So just going to verify a of 8. Well, that's 2 times 8. I'm hoping to get back to 55. Plus 72 divided by 8 plus 30. Okay, so now all we got to do is evaluate this one here. So, okay, 2 times 8, 16. Plus 72 eighths, which is 9, plus 30, which is 55. So maybe if you build a function, you want to make sure it's accurate, you didn't make any mistakes. So we just verified it. And we said x lives anywhere from 0 to infinity. So next prompt, for what values of the variable does this problem make sense? Okay, I was ahead of ourselves, so we said x is from 0, non-inclusive, to infinity, non-inclusive. Algebraically answer the question. And this is where I asked you to put your calculus hat on. You've got this a of x formula. Could you graph it and look for the high and look for the lows? Yeah, but this is calculus class, so I'm going to ask you to do more than that. So it's 2x plus 72x to the negative 1 plus 30. So how do I use calculus here? Right? If you're trying to minimize a function, you're gonna minimize a function whenever it, if your function looked like this, when it dipped down, that would be a minimum. Right? But like always, you need to check the endpoints of your interval. I mean, what if the graph of your function looked like this? The minimum wasn't necessarily where it dipped down. The minimum is actually at the left-hand endpoint. Well, does our interval have a left-hand endpoint? No, but x can be as close to 0 as you want it to be. So what is a of x? Right? What will a of x? What's the limit of a of x as x approaches 0? Let's find out. Because maybe the way to make that green area the smallest would be to let x be infinitely close to 0. So we need to see. Okay, so the limit is a of x goes to 0. Well, this term, 2 times 0 is 0, plus 72 divided by x. Well, if x gets infinitely small, that thing is going to get infinitely big. So the limit of a of x as x goes to 0 is infinity. So is it a good idea to let x be really small? Is that going to help minimize that green area? Turns out no, right? The smaller you let x be, the larger that area is ultimately going to have to be if you're going to accommodate the 24 square inches of paper. So this is kind of that whole process on absolute extrema where you check the endpoints. And I've said sometimes you're not going to have a closed interval when you're checking endpoints, so you do it through a limit. Next we do, the other endpoint was really infinity, right? So the limit of a of x as x approaches infinity. You want to justify, you want to be able to say, here's why I would not want to let x be infinitely large. Okay, so 2x. Okay, what's 2x do as x approaches infinity? That approaches infinity. So you're kind of looking at infinity, not a value, a direction, plus, okay, 72 over x. As x approaches infinity, that approaches 0 plus 30. So what's the limit? Well, infinity plus 0 plus 30. You're looking at infinitely large. So equals infinity. So what have we shown? Well, we've shown that we don't think it's a good idea to let x be infinitely small or infinitely large. So I'm guessing something happens in the middle, right? So if this thing's going to minimize in the middle somewhere, then, well, we better check our critical points. Right? So if you're going to form a minimum, a couple ways you can form a minimum. Either your derivative goes undefined or your derivative goes to 0. So, well, I guess we better find our critical points. So the next work is we gotta find a derivative, set it equal to 0, and look at where it's undefined. So a of x equals 2x plus 72x to the negative 1 plus 30. 2x plus 72x to the negative 1 plus 30. Alright, so a prime of x is 2 plus negative 72 over x squared. Cool. Alright, that's a prime of x. So, right, a prime tracks whether a is increasing or decreasing. And if you're going to form a minimum on a of x, what will have happened is a of x will have decreased, and then it will have increased. And like we've said, if something goes from decreasing to increasing, well, in between the derivative either goes 0 or undefined. So a prime of x equals undefined when x equals 0. Well, what is a of 0? Wonder how much that is. Well, x can't be 0. A of 0 is undefined. So do we really, is 0 a critical point? Well, no. To be a critical point, your function's got to be defined there, and either the derivative goes to 0 or the derivative goes to undefined. So do we really care about when x is 0? No, it doesn't make sense in this problem. A prime of x equals 0 when x equals... I'm just going to grab my 89 and solve that. Set the derivative equal to 0. So solve 2 plus... I can do 2 minus parenthesis 72 divided by x squared equals 0. Solve it for x. When x equals plus or minus 6. And for what we're talking about, we said x has got to live between 0 and infinity. So all we care about is the plus 6. So a of 6. How much is that? Right? Well, a of 6. So if you plug 6 into a of x, you get 2 times 6 plus 72 over 6 plus 30. So 12 plus the 30 plus 72 over 6 is 12. It's 12. So 30, 40, 54. So if x is 6, if x is 6, you're going to keep the paper's area to 54 square units. I'm going to write that. If x is 6, paper's area is 54 units squared. This problem was about absolute extrema. The process on absolute extrema goes check your endpoints, check your critical points. We were looking for a minimum, so pick the smallest one. Okay, so I'm going to summarize this again. Right, so what we're going to use to make our decision on what the minimum is, we have this one here. Okay. So he said, hey, we've considered the endpoints. Critical point at x equals 6 and a of 6 equals 54. So if you compare these three things, what is the smallest? Well, 54 is the smallest. And that as a result of x being 6. So I would say, absolute min of 54 when x equals 6, 54 inches squared. Let me make sure I answered the prompt here. Algebraically answer the question, be sure to justify your answer. So there's our justification. Right here. Now, if you just said this, that's not enough, okay? You've got to show me evidence that you're checking the endpoints of the interval and you're checking the critical points. We're talking about absolute extrema. So there you go. There is take home number 8. The process really went build a function that will track what you're looking to minimize, and then initially that function was a function of x and y. I used the fact that x times y was 24 to rewrite my area function just so that it had x's in it. And then I said, hey, calculus helps me identify absolute extrema without actually looking at a graph. And that process on absolute extrema was look at your endpoints, look at your critical points. We were looking for a minimum, so we just said out of those 3 blue items, the smallest was 54, and that occurred when x was 6. So nicely done.